Now we have prepared to learn indexing techniques. So far we have not started learning indexing techniques, right? So we build foundation to understand indexing techniques. So in literature, indexing techniques are classified into different ways. That means, in an ambiguous way. Some people say that indexing can be classified into two parts. One is clustered indexing, non-clustered indexing. Some other people say that the same indexing techniques can be classified into primary indexing, clustering indexing, secondary key indexing, secondary non-key indexing. So we'll see two things so first of all we'll see this classification, this classification. These two are independent classifications. See here, clustering indexing we have here and we have here clustered indexing. But both are defined in different ways. That's why you should understand both definitions. Sir, in exam, if suddenly they say clustered indexing, what is correct? So ambiguous, that is what. So it is ambiguous. So based on the context, based on the options, so maybe the examiner might be thinking clustered indexing is this one or this one. We should predict. That's it. We don't have option. Okay. So we'll see. So some gate questions related to this clustered indexing, and we'll see how to answer them without, and how to map with really. So the examiner is using this definition or this definition, but we should agree that there is a ambiguity in the literature, right? Because your literature whatever is not specially designed for your gate exam, right? So don't think that everything is unambiguous. Sometimes some discussions, otherwise some definitions may be ambiguous because so many people define them in different ways. So there can be multiple different ways. Then your examiner asks a question, sometimes it will become ambiguous. So we don't know. So what examiner is following, right? Either this one or this one. Sometimes it happens, very rarely. So you should not bother about it, right? So only one or two questions are like that. It should not affect your exam, right? Let's try to understand now clustered indexing and non-clustered indexing. What is clustered indexing is, example, if you create index on a file, this is your file, let's say. Of course, it is divided into pages. Every time I don't tell that, we know that like this file is divided into pages and every page is mapped to one disk block. So they are all inappropriate now. So let's say this is your file, and in this file, let's say there is a field called employee ID. We say that it is key field. Okay. Otherwise, we are applying, forget about key field or not. Let's say you are applying index on this field. Let's say index field. So index field is employee ID, and your data is sorted on that employee ID field like this 1, 2, 3, 4, 5. Now you are creating index on that employee ID. Obviously, most of the times, so we also create ordered index, right? Example, let's say you have created index like this 1, 2, 3, 4, 5. This is your index. Now index on employee ID. Whenever you create index on employee ID, usually you create ordered index. Okay. Now already data is also ordered on index field. Correct. So we say that whenever your index file and data file have same order, that is called clustered indexing. The second one, non-clustered indexing. In non-clustered indexing, so opposite thing will happen. That means, example, let's say your data is not sorted on employee ID field. Otherwise, let's say your data has some order 1, 5, 4, 3, 2 with respect to employee ID. So here employee ID is what? Index field. So let's say employee ID is index field. Now this is your index. Now your index is created and the order of the index is like this 1, 2, 3, 4, 5 for time being. So this is your index on same employee ID. That is a discussion. Now with respect to employee ID, the index order is 1, 2, 3, 4, 5 and your data order is 1, 5, 4, 3, 2 and they are not same. Then we say that such indices are non-clustered indexing, right? And one more thing. Example, let's say your data is like this 2 something 5 something 4 2 1. Otherwise 2 5 4 something 1 something 7. This is your data. Now let's say somehow some weird index you created. Most of the times your index will be ordered, but it is not compulsory. What if your index is like this 5 2 5 4 1 7. So here your index order and your file order on employee ID same, correct? Then we say that it is clustered indexing. right? So in clustered indexing, the data order and index order are same. That's it. Whatever it is, doesn't matter whether it is sorted order or not, doesn't matter. But if you can ensure that your data's order and your index fields order, index order both are same, then we say that is clustered indexing. Otherwise, we say non-clustered indexing, right? So we will see. So we can, by seeing the index, we can decide whether it is clustered indexing or non-clustered indexing. Now we'll come to the second classification. In the second classification, same indexing techniques can be divided into four parts: primary indexing, clustering indexing, secondary key, and secondary non-key. So what is primary indexing and clustered indexing, we will see here in this classification. Example, let's say you have employee table with only two fields, employee ID, employee name, and the data is something whatever, doesn't matter. So primary indexing technique is a indexing technique. We say some indexing is primary indexing if it is indexing on primary key field. Example of primary key is employee ID. Let's say for your table employee ID is a primary key. Then we say that, example, if you create index on this primary key, then we say that is primary indexing. But one essential condition is your data should be ordered on employee ID. So that is compulsory. There are 2 points. I am discussing primary indexing. In primary indexing, first condition number 1. So index on primary key field, usually primary key field or key field. Otherwise, any candidate key field also sufficient. Any candidate key field. So need not be primary key. Otherwise, at least candidate key. Now, second thing, your data should be ordered. That means data is ordered but on dash field. What is the discussion? You are creating index on what? Primary key field, right? Or key, some field, right? And especially that is primary key. So data is ordered on, I say, index field. Now 2 important points. Index on primary key field. That means your index is primary key or candidate key. Now your data is ordered on such candidate key. Okay. So and one more thing. So this is not compulsory to be candidate key. At least your key should contain, some candidate key. That means your key can be super key also. That means you are creating index. That index may be primary key, otherwise candidate key, otherwise super key. So far I have not defined what is primary key, right? I will tell you now clearly what is primary key. Usually in reality, in implementation, what happens? In theory, we know what is candidate key, what is super key, right? You know the distinction. So usually super key might have redundancy, but candidate key will have set of attributes which uniquely identify the table. That means candidate key usually doesn't need to be repeated, right? And it is minimal set of attributes. Now in a table, sometimes you want to identify a unique attribute set, correct? So that you want to make it a primary key. So primary key is nothing but a key, an attribute set, otherwise a group of attributes which are generally unique and not null, correct? That is primary key concept. What we do is, generally we pick one candidate key as a primary key in the real world, because it has that property. Candidate key has some property. What is that? It is minimal set of attributes which are generally unique, right? So that's why we can make candidate key as primary key, but there might be multiple candidate keys in your table. One of them you should make primary key, because only one primary key is allowed to create. So there is no purpose of creating multiple primary keys. Okay, so that's why, so one of the candidate key usually will be picked as primary key. That is the difference between candidate key and primary key. Theoretically, anything can be candidate key, primary key, any candidate key. But we have to fix something. Usually, example, let's say your table contains two unique identifiers. One is employee ID, which can be primary key. Second one, let's say Aadhaar card number. Every employee has Aadhaar card number. That is also unique, right? And not null. So there are two candidate keys here. Aadhaar card number is a candidate key of your table. Employee ID also a candidate key of the table. Any one you can pick. Understand? So that's why when you have multiple candidate keys, so people prefer, anything, usually we prefer employee ID, right? But there is a trade-off. You can keep anything, not a problem. I don't want to discuss that, but I want to say finally, primary key is one of the candidate key which is really fixed as a primary key. While creating the table, if we want to make one attribute set as primary key, then we have to pick one of the candidate key. That is sufficient at this moment. Now we will come to our concept, that is primary indexing. In primary indexing, your index is on usually primary key. Again, there is in literature there is ambiguity. Some people say that index on only primary key. Some people say that index on super key. So just doesn't matter. Finally, the idea is the index should be on a set of attributes which uniquely identify the table. That means, so index is on attributes which cannot contain duplicates. Okay, that you remember. Next, data is ordered on index field. Let's say your data is ordered on index field. That means, example, you are creating index on super key or primary key, right? Let's say this table has a super key or primary key. Let's say employee ID. Let's say employee ID is a primary key. Then if I create index on that primary key, then we say that it is primary indexing. So data should be ordered on that index field. Index is employee ID right now. Then your data should be ordered. Yes, already data is ordered. Then I can create. Such index is called primary indexing. Now second one is clustering index. In clustering indexing, everything is same, but this time index need not be on super key. So index on non-key field. Let's use a word called non-key. So non-key means which is not a super key. Okay. So index on non-key. That means, so what we do is, in theory, in a lot of ambiguity is there. That's why what we do is we try to understand the purpose. Finally, if you want to create index on a field which might have duplicates, that is a concept. If any, let's take one example. This is employee ID and employee name. So in this table, some attributes may contain duplicates, some attributes may not contain, right? So that's why let's use a word called key and non-key. So key attributes is nothing but set of attributes which generally do not contain duplicates. Non-key is nothing but usually the set of attributes which contains duplicates. Using this concept, I am going to define all these primary indexing, clustering indexing, everything. So in primary indexing, example, in these two fields, usually employee ID is a field which generally cannot contain duplicates, right? So on such field, if I create index and data is ordered on this employee ID field, example, your data is like this 1 2 3 4 5. So point number 1, finally data is ordered on dash field, on key field, otherwise index field. I can say data is ordered on index field is the one condition. Second condition is your index is on key field. Index is on key field. Then we say that is primary indexing. You remember always these two important points whenever you try to understand primary indexing. Step number 1, your data is ordered on index field. Let's say you are creating index on employee ID, then data is ordered on index field. Yes, data is ordered. Second one, index is on key field. Yes, index. What is index now? Index on employee ID field, right? That is key field, correct. So that's why this is called primary indexing. That means if you create index on this file, it is primary indexing. Now we'll see second one, clustering indexing. In clustering indexing, the idea is same. Data is ordered on index field. Okay, so that is compulsory. But here index is on non-key field. Non-key. That is called clustered indexing. Otherwise, clustering indexing. Now we'll see secondary key indexing, secondary non-key indexing. So slowly you are realizing that indexing can be on key, otherwise non-key, right? If index is on key and data is ordered, primary indexing. Index is on non-key but data is ordered, then clustering indexing. Example of clustering indexing is like this: A, B, C, D, E. Okay. So let's take data here, something 5, 4, 2, 3, 1. Now, example, let's say if I am creating index on employee name. See the details. Data is ordered on your index field, correct? Yes, A, B, C, D. Data is ordered. Second one, index is on non-key field. Yes, employee name is non-key field because it can contain duplicates. That is what the property of non-key field. Yes, we are absolutely right. That's why it is clustering indexing. Now secondary key indexing. So secondary means your data is not ordered, remember. So here secondary key indexing is nothing but simply data is not ordered on dash. on index field, whatever the index field. So that is one important condition. Second one, so now let's focus on secondary key indexing. In secondary key indexing especially, so index field is key field. Okay. So similarly we can define secondary non-key indexing. Data is not ordered on index field, and that index field is key field. That means the key field or index field doesn't have duplicates. That is secondary key indexing. If you are creating index on non-key field but data is not ordered on that non-key field, that is secondary non-key indexing. Now I can say that primary indexing is related to secondary key indexing. What is the difference between these two? In primary indexing data is ordered. In secondary key indexing data is not ordered on key field, but here in primary indexing data is ordered on key field. Now clustering indexing versus secondary non-key indexing, both are indexes on non-key field, but in clustering indexing data is ordered on non-key field, and secondary non-key indexing in that data is not ordered on non-key field. That is the only difference. So now we are going to see clearly what is primary indexing and how to construct it, and clustering indexing, how to construct everything, all these four. Now let's begin with primary key indexing. So we know the basic definition of primary key indexing, but how to create such index we will see. So this is your data, employee ID, employee name. I am assuming that let's say this your data is divided into some logical pages P1, P2, P3, P4. So that pages are going to some corresponding disk blocks, right? Now question number one, what is the difference between page and block? There is no much difference, right? Page is our logical idea. That means, I already told you that. So there are two parts of the DBMS software. One part deals with pages, second part deals with blocks. So that is disk space manager. So one part who deals with these pages will just divide your file into pages. Now there is another part of DBMS software that actually places these pages into disk. So that is disk specialist, disk space manager, who will convert these pages, otherwise who will transfer these pages to some blocks. That is the only difference between page and block. Okay, so that means there is no major difference between them, right? That's why sometimes I use page and block interchangeably, and in the exam also, in questions also, sometimes they directly say blocks rather than pages. You should get adjusted to this kind of things. Okay, now let's begin. So in primary indexing, what we do is we just create only one entry. Now I am creating primary indexing. So in primary indexing, I create a page, first of all, one page. On that, I try to write some entries. What are they? They are nothing but the information about each block. Example, let's say this is block number 1. So I'm saying, see, block, but actually it is page, right? So I can use block and page. However, every page is going to some block. That's why I can say either block or page. Whenever I say block, that means I am dealing with low level details. If I say page, I am dealing with high level details. That's it. So we can use anything, not a problem. Let's use pages, otherwise blocks. Let's use pages, not a problem. So first of all, in every page of, I am talking about index pages. In index pages, I am writing like this: employee ID and the page number where it resides. So example, in the page number 1, so first record is what? 1. That only I write 1 comma page number 1. Now after that I write another entry that is nothing but this information. In this page, what is the first record? That is enough for me. I will tell you how to access 2, 3, 4 using this index. 5 comma usually. So where is 5? 5 is in page number 2, in that way. I am assuming that, let's say, so any file is divided into logical pages. Right now this page is full. Then I will create another page. So I am creating this index means what? I am software. What software? This high level software which creates index, right? So I am just talking about how a software creates index, right? Now second one. So here that software should put some pointer to this block, right? That is P3. So P3 starting records employee ID 9 comma P3. Since we are creating index on employee ID, so that field we use. So 13 comma and what is the pointer? P4. In that way, these page numbers are actually pointers to the pages. Now, so using this, how you access this data? Please tell us. Simple. Now example, user, some user want to access some record called this one, like 1 comma something, like example he write a query like this, select, he wants everything from select star from employee where employee id equal to something 1. Once he writes it, then this query will be evaluated by some software, DBMS software. That DBMS software will understand that it is employee table, then it will consult employee index. First of all, it will come to index if there is a index. So somehow your DBMS, DBMS software will understand that there is an index because you create index, right? So that is called metadata. So every DBMS will search, first of all check this metadata. That means what is the essential information about this table, whether index is there or not, and what are the other information, everything. So in that metadata it will see and it will realize that yes, there is an index, and especially on this employee id field. So directly, because you are searching for records with employee id equal to 1, directly will come to index, right? That's quite obvious. Now we search linearly like this. We write a software, so there will be a software which will do scan. I can say almost it's like a scan, but we stop whenever we get the right record. Example, start here 1. So 1 is nothing but our employee ID. Yes, it matches. Then immediately go to page number 1. This index says that your employee ID 1's record is in page number 1. Go to page number 1. But how to go to page number 1? Page number 1 is our logical imagination. But really it is stored in disk in some place. But how do you know that? You just consult disk space manager. My dear disk space manager, please convert P1 to a write block. Then it will be converted. Once you get the right block, then that will be transferred. When you transfer it, that takes lot of time. So far all these things are I mean just comments which are not using the data of the disk, correct? So far we are not using the data of the disk, but see here we use the data in the disk, right? This page is also stored somewhere in the physical disk, right? Let's say that is B5, that is B6. We will see the complexity, otherwise cost of this entire thing. First of all, we'll see the idea. First we come here and we take the page number 1, and you know that given page number 1 we can find out the right block, and we'll come there and just we transfer that to buffer, right? So in main memory buffer we keep it 1A, 2B, 3C, 4D, and we search, because only in main memory we can search, right? So we have a software which will search it and it will find out here, and this record will be searched. So finally my question is, how many blocks you have to transfer to the disk, to the main memory? See, this page is nothing but one block, right? This is you searched, right? To search it, definitely we have to keep it in main memory again. So this block you transfer to the disk, main memory, and this block you transfer to the main memory to search for this record. I can say that 2 block transfers. Now let's search for an employee record 16 comma d. Let's say, what if usually query is like this, employee id equal to 16, then how search will go on, we will see. First of all, your 16 matches with 1? No. We know that the first record starts with 1. That means, first page contains records, I mean which starts with 1, right? 1 or more than that. But it doesn't mean that we will get 16 here. That's why we'll go to the next index and we'll cross check. Second page starts with 5, so definitely 16 is not in between 1 5, so don't go to page number 1. It doesn't mean that your 16 is in page number 2. It is not guaranteed. That's why continue the process. I'm just giving the logic first of all, right? So 9, is it 16? No. And where will be the 16? Maybe in P3, otherwise in the next page. That's why better first you consult the next page. 13, since 13 is still smaller than 16, it means that definitely P3 does not contain 16. Why? P3 starts with what? 9, and P4 starts with 13. That is what just now you realized. Really P4 starts with 13, then P3 cannot contain 16 because data is ordered. That is the thing we can exploit here, and quickly we can find out the records. So far we are just searching in your index file, right? 1 5 9 13. So we reach, example, let's say after this one 13 there is no record, means it is null. I mean somehow the software realizes that the next is, so 16 is definitely after 13 because there is no further record to search. This is the last record in the pages, so directly we go to P4. If and all if there is a 16, it will be in page number 4, and we come here and transfer that into main memory and search it. So it will be here and you get it. So finally we can output like this. My dear, the user who wrote this query, answer is 16 comma D. So what is the time complexity here? See, from now onwards I am ignoring that number of records in the table, otherwise sorry, in a page, and the record processing time. Usually record processing time is nanoseconds. It is negligible. That's why we can take that entire parameter as 0. That's why it doesn't matter. In our previous calculations also, so many times we used R and C. Actually they are negligible, so it doesn't matter if you don't understand them. Okay, so only major thing is block transfers. We should understand block transfers clearly. How many blocks we are transferring? For searching 16, this one you transferred, right? This is a page which is residing in disk, correct? We have to transfer it, and we have to transfer this one 1 2, then you came to this page. For that, so this page also we have to search. For that again transfer. So I can say that 3 disk transfers, right? This one, this one, this one. Did you touch these things? No, we never came to that pages, right? So I can say that 3 disk transfers. From now onwards, disk transfer calculation is very easy. How? Number of pages you are searching, you just find it out, equal to number of disk transfers. So now in the worst case, so you might require 3 disk transfers. Why? Your indexing contains only 2 blocks, right? Then you never search more than that, correct? So 2 blocks you might search in the worst case, plus 1 block which is in the main file. So 2 plus 1 always, not always, in the worst case. In the best case, you might get your record here. And so minimum, I can say in this problem, especially for this one, minimum 2 pages you will search, and maximum, in this example I am telling, don't remember them, maximum 1 2 and 1 data page. So finally 3 pages. Here 1 plus 1, 2 plus 1. So this one is data page, this one is index page. Here 2 index pages, 1 data page. So this is a concept of primary indexing. You don't see the advantage of this primary indexing for small set of pages. Like you are, after all, your page contains only 4 records, right? Then how can you see the advantage? And one more thing. So you might have this question, why this page has 4 records and why this page has only 2 records? The reason is, here the page has different structure, sorry, record has different structure. So in each record you have employee ID, employee name. So what we can assume is, let's say this employee name size is byte, okay, and this page number size might be different. So page number is nothing but an address, right? So an address of a page. So we might have 4 byte addresses, let's say. If that is the case, then here there is a difference. Employee ID same, but here employee name is only 1 byte, but page number is 4 bytes. Usually, then number of records here will be less, right? Because the size of each record is bigger than size of each record here in the main page, correct? So that is one thing you should observe. Now, in this primary indexing, the important things are, what is the main property of the primary indexing? 1. So your data is first of all ordered on key field, and second one, we are creating index on that same key field. That is called primary indexing. One more important observation, usually, since for every page you are creating only one index entry, then if say, let me say that these are all records of the original file. The number of records in the original file, let's say something X, then the number of records in your index file will be definitely smaller. The reason, we are not creating every record per every record of the main entry, correct? So for every page, you are only creating one entry, then the number of records here will be definitely smaller in size, correct? So that is what one important point you should realize. Now we'll see one question, numerical question related to this primary key indexing. Okay, let's see this problem. Consider a file of 65,536 records and each of size 64 bytes, and key field size is 10 bytes and block pointer size is 22 bytes. Assume that block size is 256 bytes. Stop the video and read the details clearly. Then you try to answer this question first. The number of blocks required to store the file. So here one important point is, what is a block size? 256 bytes, correct? Usually when you have a block of size 256 bytes, we should check whether records are completely filled. That means this block is completely occupied or partially. What does it mean, sir? I will tell you. Example, in this problem the record size is 64 bytes, correct? Since record size is 64 bytes, then the 4 records are going to be sit in this block. and there is no empty space. Sometimes what happens, example, let's say your record size is just 50 bytes. If it is 50 bytes, then what happens? Then after keeping 5 records, 55 is a 250, then you get some empty space, right? That's 6 bytes. Now the question is, sir, should I keep the next record? How can you keep? Because your record size 50 bytes. You have empty space of only 6 bytes. What we do? So what we can do is two alternatives possible. One alternative is keep that 6 bytes or something and go to the next block and write the remaining record. That means I can say that your record is spanned into two blocks, right? Some 6 bytes here and some 44 bytes here almost. And we keep the pointer like this. That means after this block, your next block is here. In that way we maintain the linked list of blocks, of course. So usually we do that, so whenever you are searching for the data, then we search this block, later we search this block, doesn't matter for us at this moment. Finally, sometimes your record might go to multiple blocks, correct? That is one organization. The problem with this organization is if you do that, so example, for especially for this record, unnecessarily we have to search two blocks, right? That means there are two block transfers. So when you optimize everything, then every bit, every inch you have to optimize, correct? Then what we can do usually, so example, this people are searching for this record, then they require two block transfers because they have to fetch this page, that means this block and this block, right? So that's why there is one more organization possible. What is the solution? We can go for another organization, that is called unspanned organization. So whatever we discussed, it is spanned. Okay, now in unspanned organization what we do is, so though there is a wastage of space, we ignore that remaining part. So only we keep full record, otherwise nothing. Example, let's say your data block size 256, but this 6 bytes I cannot use because effectively currently in this my file record size 50 bytes, then only I keep 5 records, especially for this problem. Then this 6 bytes let's keep aside and simply say that it is invalid data. Then remaining record, whatever full record, you keep adding into second block. This is block number 1, then write in second block. So I can say that there are only 5 records here, 6th record goes here, correct? In the previous example, the 6th record was going here and here, it was occupying multiple blocks. So that is spanned organization. In spanned organization, record occupies multiple blocks or two blocks, and in unspanned organization each record goes to only one block. So here we are wasting the space, but trade off, so we are saving the time. So to fetch this record, any record, we require at a time one block transfer, but in span organization sometimes to fetch a record you might require multiple blocks, isn't it? So that is the difference, or two blocks of course, especially. Now let's come to our problem. In our problem, so since your block size 256 is divisible by your record size, so 64 for the 256, that organization doesn't matter, like whether it is spanned organization or unspanned organization doesn't matter, because so your records are perfectly fitting into a block, no wastage, right? When there is a wastage, that these two models comes into the picture, but there is no wastage. So exactly, effectively 4 records I can keep, right? So it is like I can say unspanned organization, otherwise spanned. So this kind of problem comes under anything, right? So in any way, finally there will not be any problem for us. So now how to calculate this solution? The number of blocks required to store the file. What I do is, first of all, it is always better to follow this technique. Ask a block, my dear block, what is your capacity? 4 records. Remember it. Now we'll extend our problem to 65,536 records. So in a block, if you can 4 records, then how many such blocks are required to store your file? Very simple question. It is an aptitude question. So divide your number of records by the block capacity with respect to records, 4 records. If you divide it, example, why it is correct I will tell you. Example, there are 20 records. Then how many blocks are required? Since a block can occupy 4 records, 20 by 4. Similarly, 65,536 by 4. Then it would become 464s. I can, sorry, not 464s, 416s, 64, 115. So it will be 16,384. Okay. So this is a solution. Number of blocks required to store the file is 16,384. Now we'll come to the number of blocks required to store the index file, especially it is primary indexing problem. If it is primary indexing problem, we should recall. So what is the structure of your primary index file? So how you are doing recall? In a primary indexing, what we do is we create entries in the index file. One entry for one block of the original file, correct? That is the important concept you should understand. Now these are all the blocks of your main file, but already we calculated in the main file we have 16,384 blocks. Then there will be exactly 16,384 entries, that already I taught you. If that is the case, the number of entries in the index file is 16,384. I can say that this index is a file, correct? If you ask me number of records in this index file, I say 16,384 records. It is directly one-to-one correspondent with this number of blocks of the original file. Now, but I want what? I want number of blocks required to store the index file. For that we should know the record size here. So this index file has a different record size. Why? What is the record entry in this index file? In this index file, record entry is like this. We store key comma usually block pointer, which points to the block, correct? So what is the block pointer size? It is mentioned that in the problem the block pointer size is 22 bytes, right? Now what is the key? Key field size is given as 10 bytes. So finally it is occupying after all 32 bytes. Since your record size is 32 bytes, you have 16,384 records, you remember. Now we'll come to the same idea. What is your block capacity? This time it will be different, because you are keeping different records, right? Different structured records. So here what is record size? 32 bytes, remember it. So the capacity is 256. Now first of all we'll ask, my dear block, how many index records you can occupy, you can accommodate? 256 by 32, it is 8, obvious, because it was 64, now it is 32, then the occupancy will be increased. So it is 8, remember it. Again it is proper divisible, right? 256 is divisible by this 32, then whether the organization is spanned or unspanned doesn't matter. Whenever it is not properly divisible, we should think about spanned and unspanned. We will see in the next problem. At this moment there will not be any problem. You realize the capacity of one block. What is it? How many records? So just 8 records, right? Remember it. But how many records we have in our primary file or index file? 16,384 records. Same story. You have 16,384 records in the file, and your block capacity after all 8 records. Then how many such records you want? It will be definitely 16,384 by 2 cube. Actually 16,384 is 2 to the power of 14. So it would be 2 power 14 by 2 cube, which is nothing but 2 to the power of 2 power 14 by 2 power 8 is 2 cube is 2 power 11. So answer is finally 2 power 11 is 2048. So 2048 blocks. Yes, we got it. Now let's compare them. Usually you require 16,384 blocks, but now you require only 2048 blocks. Sir, so what? What's the advantage? From now onwards, if you use primary indexing on this data to search, in the worst case what happens? You search index, right? How many blocks index contains? 2048. In the worst case, every block you have to search. So 2048 blocks plus. After that we will find out the right record and we'll go there and we'll find out in the original file. This 2048 for searching the index file, and this one for searching in the main file. End of the day we search in the main file, correct or not? We after taking the right pointer. For that you should understand how indexing works, primary indexing. In primary indexing, whenever you get right pointer, example you search like this. Suddenly you get right pointer and we take it and we directly go to the data and we take the data. There one block transfer. And in the index, in the worst case, how many entries you check? You might require to check all the entries. Sometimes in the worst case, that takes after all 2048. On average we can do like this. On average what happens? So your right index will be middle. Since 2048 blocks you have, then the right index will be in middle. That means in 1024th page on average, just it's a calculation, mathematics, 1024 blocks to be searched. then you get it. Once you get it, take the block pointer and go to the block which is file block, original file block, and there you search. If it is there, it is there, otherwise it is not there. But whatever, we have to only search that block. Then you require one more block transfer. Finally we are calculating number of block transfers, 1024 plus 1 on average case. Previous one was 2048 plus 1 worst case. In that way, best case is obvious, unnecessary. In the best case, first entry itself is your right entry. Then you take and go to the block. Then here one block you are searching and one block in that. So two blocks, correct? So 2 is best case, 1025 in the average case. In worst case it is 2048 plus 1, 2049, right? So this is about this primary indexing problem. Let's see one more indexing type, that is clustering indexing. Clustering indexing is indexing on non-key field. So that's why what I do is, in this data I take employee name as the index field. So here that's why we need employee name and block pointer. So how we are going to create the index, we will see. There are two techniques. Of course you can follow blindly primary key indexing technique. What is that? For every block only create one index. Yes, it might work, right? So we'll do that. What you do is, first of all take the block number 1, right? So especially maintain this index in this order, like block 1, after that index for block 2, after that index for block 3, after that block 4. That means in data order. So B1, what is the employee name on that? That means top record A, right? Next B2 block and index, first record's name is B. Then B3 B. So B4 we can keep E, correct? Now how to search for some record, we'll see. Example, you are searching for A. Simple. Go to B1 directly and search. Since data might be repeated, so maybe you should see the previous block and next block. Remember it. I will tell you the reason. Example here. So B1 starts with what? A, right? So the next pointer shows that there is no next block, otherwise previous block. That's why don't require to check. So you now only retrieve here 1A, retrieve it. After that, suddenly if you see B, then in other blocks, that means succeeding blocks will not have anything, right, related to A. So since data is ordered, we can exploit that situation and we can say that these are the only valid records. In that way we can plan our algorithm, otherwise technique. Now B1 is done, A is done. Now example, you are searching for, let's say, D. How to search for D, we will see. First of all, I will look for D in this index. A, since A is less than D in lexicographic order, I will come here. Since B is less than D, then I will try to go for right side. So here it is again B, correct? So B, is it not less than D? Yes, come here. E, it is greater than D. That means we understand that your D, if and all if it exists, it will be in between B3 blocks and B4. That means definitely in B3. Why? Since B4 starts with E and B3 starts with B, then if and all if there is a D record, it should be in B3 block. Then I directly go to B3 block and I search. Okay, so here you get it. And you remember one thing, since data is ordered, once you transfer this data into main memory, we can apply binary search again there also, because data is ordered. So your data is ordered on this employee name. So apply binary search. And one more thing you remember, same binary search in primary key indexing also. So you can apply binary search for your record. Once you reach the right block, in that block data is ordered, then whenever you want to search for a particular record with key value, using that key you apply binary search. Okay, so in that way we can optimize. So finally you got it. Example, let's say you are searching for F. A, B, B, E. Since after E there is no record, that means if and all if there is a F record, it should be in B4. Go to B4. E. The starting record is E, right? Then what to do? So take the next one. Yes, it is F. Continue, because there are duplicates. There might be other records which are consecutive at least, right? F. Then G, stop it. Sometimes what happens? What if this record is F? Think about it. If this record is F, then your entry will say that B4 begins with E, correct? So example, this is also F. Think about it. Let's say this entry will be F. I am doing the modification. So I am writing here F and F. So if that is the case, then what happens is B4 will come to F, then that is B4. You search here only, right? Then after that you say that F, 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 and you retrieve these three, and once you see G, then you say that it's done. But whenever the first record of your data, otherwise your block is F, then definitely there might be some other records in the previous block. That's why if you use this technique, you search always previous blocks and successive blocks. That you should remember, next blocks and previous blocks for any entry. What I want to say is, first of all, identify the suitable entry, come to that whatever it is, then search in this block and previous blocks and next blocks, anywhere data can appear. That's it. Okay, so but still it works. Sir, but we are searching a lot, right? Yes, because you have that many records, because your records are spanned over all that blocks. We have to search, we can't escape. How can you escape? Example, your records are all spanned in total blocks, we have to search it, we can't escape. Now this is one technique. So the second technique is, so apply otherwise keep an entry only rather than blocks. What we can do is keep an entry for every distinct record, so that we can create index with all the distinct key values. Okay, that is also possible. Let's do that. So what I want to say is, for every different employee name, you simply create a index. Example A. What is the first record with A, which is in B1, right? That means for A is in B1. Now what is the next distinct record B? Where it is? What is the starting point? B starting point. Only maintain the starting point. B starting point is B1. Next. What is next one? C. Where is C? C starting point is B3. Next. What is the next record here? F. Where is the starting point of F? Starting point of F is B4. Where is the next record? G. Distinct record. G's starting pointer is B4. In that way we maintain. Maybe index size is a little bit bigger than previous one, right? At least this for this example. Doesn't matter. Now we'll see, if you use this technique, what is our logic? We are maintaining the starting record of every different employee name, right? Example, you want to search for something called F. Then you directly come like this. Everything. Really in this index, if there is a name F, then definitely you can search. Example, let's say the record is D. You want to search for D. If it is not there in index file, it cannot be there in this file, correct? Because for every different value you are keeping the index, right? In that way. So D cannot present here. Now example, you are searching for F. Come here like this, A, B, C, F. Take B4. Go to B4. Where is B4? This one, right? Since we know that B4 is the starting block in all the blocks, I mean where F is stored, then we start here and we don't go to previous blocks, directly we go to successive blocks. F. Suddenly you got G, means what? You don't require to search for other blocks. In that way we can design the logic based on how you arranged your index. That's it. So there are multiple ways of creating clustering indexing. Okay, so the popular one is this one. Usually people do this way, but other alternatives also possible. You should understand. That's why, so they, in GATE exam there is no GATE question. I mean there is no question related to this clustering indexing, because multiple ways it can be defined. Now we'll try to use this technique. Example, let's say you are searching for C. A, B, C. We get it and come here B3. Directly go to B3. Right? Now we know that if and all if C exists, the starting block is B3, right? Search here. We can apply binary search, not a problem. And we get it. Once you get it, go to the successive records. Since the next successive record contains F, we can stop it, right? So this method also will work. So this is all about clustering indexing. Now the question, when already you have primary indexing, can we create clustering indexing usually? The question. It is impossible. Why? I will tell you. Primary indexing and clustering indexing. My assumption is already you have primary indexing. When you have primary indexing, your data is, for that your original file should be ordered on, I just tell with example, employee ID is a primary key, right? So on employee ID, let's say you are creating primary indexing. Then when you create it, then your data is ordered on employee ID field, right? Now the same data cannot be ordered on other fields, but because whenever you create clustering indexing, we need data which is ordered on other field, non-key field, right? So what I want to say is, at a time your data cannot be ordered on primary key field, otherwise key field and non-key field. How it is possible? Because one set of data can be ordered on only on one field at most. That's why when you have primary key indexing, but both indexing techniques requires order of the data. So and on different fields. That's why primary key indexing or clustering indexing, only one is possible at a time. You go for either primary indexing, otherwise clustering indexing. Sir, then I want two, sir. Why? There are some queries in my requirement. That means my users are writing 50% of the times these questions. What is that? Select something from employee where employee ID is something like this kind of question they are writing. That means they are referring employee ID 50% of the time. So remaining 50% of the time their queries are like this: select star from EMP where employee name is something like this. Otherwise, whatever they are writing condition on employee name. If that is the case, then you have only primary key indexing. 50% of the time your query will be like this, then you get benefit, right? But since you don't have clustering indexing, then this kind of queries, for that, since there is no indexing, we should go to the file and we have to scan from start, right? Example, I want to know employee name Raju. Then we have to search the file, right? Of course you can apply binary search, but that will not have much effect because indexing is faster. So we will see, already I told you why indexing is faster, but we will see one mathematical problem where you will see the difference between simple binary search and indexing technique. Like we can see the difference. So definitely indexing techniques are faster. The reason your index file size is smaller than your original file. Okay, so we will see of course the details. Now let's see one question here. Example, some student asked this question, imaginary student. He's asking like this: sir, I have a file. Fine. There are 2 power 30 pages. Fine. That means page means block. Both are same. That means 2 power 30 blocks. Okay. Then why should I create index? Why don't you apply binary search on this? Let's say since your data is ordered, right? When data is ordered, why don't you apply binary search to find out the right record? Yes. So binary search requires how much time? Log. So I'm just focusing on number of disk transfers, right? Since there are 2 power 30 pages, to search it, I told you the technique. Go to middle, then after that go to left page or right page. In that way, at most log 2 power 30 pages you have to search, correct? So the number of block transfers or page transfers are only log of 2 power 30, that will be 30, right? So that is what students argument. So 30 page transfers are enough, right? Then why we have to create index? Even 30 page transfers is huge. And when you create an index, generally we go for, most of the times, almost we go for ordered index. That means what? We create index also as a ordered file, right? We have seen it. Example, it is primary key indexing. In primary key indexing, so we create index on employee ID field, it's example, and block pointer. So in index I have created my index like this, right, as a ordered data, right? 1, and we create example, here it is 1, this is let's say 20, this is 30, these are all the employee IDs. Then your index looks like this: primary index 1, then 20, then 30, right? For every block one entry, we know that. Then this index size will be definitely smaller than your original file. Why, sir? Because the two reasons. One is, for every block of your entries there is only one entry here, correct? Example, your block or page contains 1024 entries in your file. That means your page size is 1024 records. Then there will be only one record here. So that's why 1024th size will be reduced. Otherwise your file, this file, index file size will be 1000, original file by 1024, rough approximation. Second one, your file might contain multiple columns like employee ID, employee name, salary, age, followed by some image, right? Sometimes your file might contain binary large objects. What is BLOB? Is binary large object. Binary large object is nothing but usually an object, otherwise it's I can say field, which contains image, otherwise video, right? So such kind of attributes will have very big size. Okay, example, let's say one employee has image is one data type, let's say. Then that image will have 1024 KB, otherwise 1024, whatever, maybe bytes, whatever. Because of that huge size, then your file will be very big. But here this index file doesn't contain that binary large objects. Why? Your index after all contains key field and block pointer. That's why whatever the way you see, in any way finally this index file size will be smaller. So what, sir? I am applying here binary search. That is what student argument. So if you can apply binary search here in the big file, since index, if you create index, it contains, let's say, assumption 2 per 20 pages. Your original file contains 2 per 30 pages. Then index file contains usually 2 per 20 pages. It depends, of course. We can calculate it. Then that 2 to the power of 20 pages are ordered, then we can apply first of all binary search here, correct? If you can apply there, I can apply here. So it takes only log of 2 to the power of 20 page transfers or block transfers, correct? So only 20 block transfers. Then once it is done, you get the right pointer to the block where your data resides, and you know the technique. Once you do indexing, once you search index, once you get the pointer, then directly we should go there and directly we should get the data, because that block definitely contains it, right? And you don't further need to search, especially if it is primary indexing, correct? For such kind of thing, then definitely this 20 plus, after all, one block you have to search, which is from main. So only 20 plus 1, correct, where it is 30 blocks. So definitely 20 is better than 30, correct. So after some time we are going to see some more indexing techniques like multi-level indexing. Once we learn multi-level indexing, you understand that, so we can further reduce the number of block transfers for any search. Example here 20, right? 20 block transfers, or 21, we can reduce it to 5, otherwise 3. That is our target finally. You remember one thing as a thumb rule, that is, so finally our indexing goal is within whatever the big file it is, within 5 transfers, otherwise within 3 block transfers, or I mean it's a range of 1 to 10. Within 1 to 10 block transfers, you should be able to search a file. That is what our goal, right? We can achieve it by after learning multi-level indexing. Second one, B trees and B plus trees. So once you learn B trees and B plus trees, you understand that we can do indexing, otherwise we can search a file within 5 or 6 block transfers. We will see that. Let's see one numerical problem related to clustering indexing. So let's summarize the rules about clustering indexing. So what I am following is rule number 1, index on, we know that index on, of course, non-key field. Non-key means here intention, it's a field which contains duplicates. Second one, data is ordered on this non-key field. So these two are essential, right? Now let me use assumption here is, that's fine. So there are so many ways we can create index. So one is I am following this one, index, I am creating index on, that means index entry for every distinct non-key value. So this is the technique I am following. Sir, in the exam, immediately students ask this question, sir, in the exam if they don't mention anything, what to do? So better you prefer this one because it is popular technique, right? So otherwise it will be ambiguous, we can't do anything, right? There are multiple ways in the exam. If they ask a question, so how do you, what is the answer, then go with popular way. That is the only thing we can do, right? That is the best thing from our side. So what is the best way of creating clustering indexing? Index entry for every distinct non-key value. With that we will see, like, so what is the answer? Your file size 2 per 30 records, correct? Now record size is given. First of all, we focus on question number 1. I would like to know what is the file size in blocks. File size with respect to number of blocks. I calculate like this. First of all, I ask block, Mr. Block, how many records you can occupy? I want to know how many records of original file size you can occupy. What is your original file type? Your original file contains 64 bytes records. So which are fixed size records, right? So how many such records it can accommodate? Because its size is 4096 bytes. It is very simple. Divide this 4096 by 64. Since it is properly divisible, so you get in no problem, right? So calculations will be so simple. So to 4096 by 2 power, I can say 4096 is 2 power 12, right? By 2 power 6, it would be 2 power 12 by 2 power 6, 2 power 6, done. So there are, we can give 64 records, remember it, 2 power 6. Now let me focus on number of blocks which required for storing file size. For that we should go to the number of records in original file. So how many records we have in original file? 2 power 30 records, right? So but a capacity of a block is after all 2 power 6 records. Then you have to divide that by 2 power 30. You have to divide 2 power 30 by 2 power 6. Then you get number of such blocks required. It will be 2 power 30 by 2 power 6, 2 power 24. So finally you require 2 power 24 blocks. Okay. Now we should be very careful while doing the indexing, correct? If there is no indexing, nothing, then at most you can apply binary search. If you apply binary search, then at most, so what is the time it requires? Definitely to find out one first record, there may be duplicates also, right? At least to get one such record, we have to apply binary search. It requires log of 2 power 24 blocks. That would be 24. So within 24 blocks, we can, within 24 block search, we can get the first record. So you know one thing, right? So your data has duplicates. So because of binary search, you get one such record. After that, what about other records? They will be like this, here, 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 everywhere. Maybe they might occupy multiple blocks also. Then finally I can say that it's a highly variable time. So 24 plus number of blocks your, that, example, there is a search key, right? You are searching the data with some key, right? Search key. So number of blocks which contains desired data, I can say, right? Desired data. Example, you are searching for employee name Raju. Then using the binary search, I will find out one record with Raju. Later, there may be so many Rajus in that block, in next block. Every block I search until I see a different name. So example, if there are 5 blocks which contains Raju name, then answer is 24 plus 5. This is usual technique, right? So binary search technique. But we have index, don't worry. So remember, finally our answer is file size in blocks 2 to the power of 24. Question here, second question is, how many index blocks are required? Example, if I am applying clustering indexing. Okay, question number 2 is, in clustering indexing, number of blocks required for what? Index file. So first of all, you should know the structure of your index file. In that, every record contains 2 fields. One is employee. I am assuming just employee name, just for good imagination. That may not be employee name, anything, maybe father name, maybe age, maybe salary, whatever, doesn't matter. So let's say employee names kind of field, and block pointer. Given block pointer size, how much? 22 bytes. And what is a non-key field, which is employee name or anything? What is the non-key field size that is given? Our index field size is clearly mentioned that 10 bytes. So it will be 22 plus 10, which is 32 bytes. Remember it. That means here index file record size 32 bytes. If you know this, then everything will become trivial, you see. Now let me ask few questions. How you are going to create index? What is the structure of your index? In your index, you will have entries like this. We know that in each entry size 32 bytes. Just now we calculated. But how many entries we fill? One entry for one distinct record, right? That means distinct record on that non-key field. There are how many distinct index fields we have? The number of distinct index field values in an index field, number of distinct values are 16,384. That means examples, maybe the field is employee name. Number of distinct employee names are only 16,384. Only that many times we create, entries, correct? So finally I realized that. So this is the formula I am writing here. So I am calculating the number of records in your index file. Number of records equal to number of distinct entries with respect to index field, index field, that is 16,384 records, right? So that you should understand. Sir, we did not understand. So many students don't understand it. For that I just take one example and I will tell you. So in example, let's say the field is employee name, right? So non-key field. Example, there are only 1000 different employee names. According to clustering indexing technique, for every different employee name we create index, right? If there are 1000 employee names, we create 1000 entries here. But here there are 16,384 such records, then 16,384 entries, done. Entry size also fixed, we know that is 32 bytes, remember it. Now we'll go to same technique, My dear block, what is your size? 4096 bytes. How many records you can occupy? I'm asking this time index records. So that divide that by 32, then you get the answer. So it will be 2 power 12 by 2 power 5, which is nothing but 2 power 7. Yes, I got finally number of records we can keep in this one. Each in a block 2 power 7, remember it. But how many such records we have in index? 16,384. So 2 to the power of 7 records we can keep in one block. Then to keep 16,384 records, index records, how many blocks you require? It would be 16,384 by 2 power 7. It's proportionate. That's why formula is 16,384 by 2 power 7, which is nothing but 2 to the power of 14 by 2 power 7, which is nothing but 2 power 7, which is 128. So you after all require 128 blocks, right? So let's summarize. The file, did you remember, the file contains huge number of blocks, but here after all we require 128 blocks. So you get advantage of clustering indexing. Let's see values. So your file, number of blocks in your file 2 to the power of 24. Number of blocks in your clustering indexing file is 2 to the power of 7. That is a difference, huge difference. Now we'll see how to do it. Example, let's say there is no index. Then we have to search all the blocks or all the pages of your file using binary search. At least your data is ordered, you get that advantage, right? So if you apply binary search, it will require log of 2 to the power of 24. That means 24 block transfers, correct? So only 24 pages you will be looking into. Here you will be, but in clustering indexing, if you have, then on that also we can apply binary search, then only 7. So here 24, here after all you need 7 plus one more. Why one more? Once you search indexing, you get one entry, one block pointer, and go to that block and we have to search remaining records, right? So plus not exactly one, because data has duplicates. It depends on the number of records with same key value, correct or not? So it will be 7 plus something extra. We assume that, let's say whatever you are searching, it occupies 2 or 3 blocks. Generally it happens. If you think naturally, then when you have employee names, okay, so how many distinct values you have? 16,384, right? That means each such value, like example, a value is repeated also. Example, Ramesh might be repeated 100 times, maybe 200 times, right? Maybe 300 times, and maybe at most 5,000 times. Then one employee's name repeated thousands of times, 5,000 or 10,000, then it occupies after all 5-6 extra blocks. So I can say that in the worst case, let's say, just these are all tentative values. They are not at all standard values. Don't remember them at least. So some students blindly remember 7 plus 5, 12. So finally this answer for this question is 12. It's not like that. Understand the discussion. Don't worry about the values. Okay. So 7 plus 5, 12, right? Usually. So maybe in best case there may be only one block contain that employee names. 7 plus 1, 8, right? So it's an order of, however, finally there is a difference. See, 24 versus something around 7 plus 1, 8 or 9, correct? So it's a 1 by 3rd of original value, right? So finally what I want to say is clustering indexing definitely has advantage over non-index. That means if you don't create index and if you create index, there is a difference, right?